All right, guys. So in this video, we're going to be going over section 7.1, day 2. This is a continuation to our first video where we talked about the average for the chapter 6 test. So in that previous video, we had talked about sampling distributions. What does it mean to be a parameter? What does it mean to be a statistic? What does it mean to be an unbiased estimator? What is a sampling distribution, all that kind of stuff. So if you haven't watched that video, make sure to go watch that first. But this one is kind of a continuation on that. So it's, again, same thing. How did the chapter 6 test go? Today we'll be taking a sample from a population, and we'll use the average from the sample to estimate the average for the population. So it says, yesterday we looked at a very small class of students as a population. In reality, there were many students who took the test. So take a random sample of 5 students and record their scores, then find the mean. Repeat this for a total of 4 times. So I've gone ahead and I've created a kind of like a mock class. So we've got a class of 30 students numbered 1 to 30, and then we've got their test scores. So 80, 90, 83, all the way down to the last one made a 77. So these are all the test scores in a class of 30, right? And it's asking us to take a random sample of 5 students and then record their scores and then find the mean. So you can do this, again, you can do this in a multitude of ways. Random number generator. I'm going to use my calculator. So if I go math, go over to probability, and I'm going to go down to randent no rep. That way I don't get repetitions of the same person. My lower bound, I've got numbers from 1 to 30. So lower is 1, upper is 30. N is the number of numbers you want. So I want 5. I'm going to hit paste, and then I hit enter. All right. And so it gives me a set of numbers, 1, 13, 10, 30, and 26. So I'm going to go back to my list, 1, 13, 10, 30, and 26. So in that case, I got 1, 30, 10, 13, and 26, okay? So each of these test scores that are associated with those numbers are the ones I'm going to be looking at for this one sample. So I've got 80, 93, 87, 80, 93, 87, and then I also had 83 and 77. And so if I average those together, I'm going to get 84 as my mean. All right. And so what you can do is, if you would like, you can take a second and practice that. You can pause your video right here, do the random number generator on your calculator, and see what samples you get. And typically in a traditional class, we will be able to, each individual student in the classroom will be able to get samples of size 5, find 4 different sample means together. And then after you do that, what we would do is we would just look at it together, and I would ask everybody, okay, what were your samples that you got? But because this is virtual, we're just going to have to pretend that we're doing that. Because on question 1, it says write each mean on a different sticker and put the stickers in the appropriate location on the poster at the front of the room. Copy down the dot plot that is created on the poster. So typically we would do this as a class, but I went ahead and made one on my own. And y'all can just copy it after it's been made. So I had sample means ranging from 68 all the way up to 94. So I'm going to create a number line ranging from 68 to 94. So I had 68, 69, 70, 71, 72. All right, so I've got little tick marks, and you don't have to number each one. You just need to kind of keep it symmetrical. So I'm just going to number every other one. So 72, 74, 76, 78, 80, 82, 84, 86, 88, 90, 92, and 94, right? And so I'm going to put a dot for each one of the simulated sample means that I got, okay? So I had one dot at 68. I had one at 71 and 73. I had one at 75. I had two at 78. Two at 79 and 80. I had three at 81. I had four at 82. I had one at 83. Two at 84. One at 85. Three at 86. One at 87. Two at 88. One at 90. One at 92, and one at 94. All right, and don't forget, you always got to label, you always got to name it. So this one is simulated sampling distribution of X bar. Simulated sampling distribution of X bar. All right, so each one of these dots represents one simulated sample of 5 different students. And depending on where on the number line it is, tells you what that average was. So for example, this one right here, okay, this one right here is a simulated sample of 5 students or 5 scores with a mean of 73. All right. Okay. Now, it's number 2 says, what does each dot on the poster represent? So just like I was writing out in this blue right here, just in a more generic, more general term, each one of these dots is a random sample of 5 students and the mean test score calculated for that sample. Okay. Now it says, what do you think the true Chapter 6 test average is? All right. Now, if I am trying to estimate the true value, I can use my sampling distribution, okay, my simulated sampling distribution of X bar to help us estimate that, right? Because remember, typically you don't know the population's true value of something, all right? If you're dealing with numbers or like individual populations with individuals in the thousands or tens of thousands, it would be near impossible to be able to actually capture all of that information. So this sampling distribution can help us estimate that, all right? So if I'm looking at this distribution, I might say it's somewhere around like, I don't know, 81 or 2, something like that. Might think it's about 82, let's say. So maybe about right here. Okay. So it says number 3, what do you think the true Chapter 6 test average was? I'm going to say it's about 82. Okay, I can't really tell for sure. Okay. Now, the actual value, the actual true mean. Okay, here, let me check my calculator again. The actual true mean in this case was 82.7. Okay, so they're not exactly the same, but they are close enough that it's an unbiased estimator. Typically, if we took a larger sample size, we might have had a more accurate number here, but because they're so close, I would consider this unbiased. Okay, because it's an accurate representation of that population mean. Now, remember number 4 says a sampling distribution shows the mean calculated from all possible samples of size 5 from the population. Is the above dot plot a sampling distribution, and explain? So remember, it's got to capture all possible samples of size 5. So here we have, how many dots was it? 30 dots. We have 30 samples of size 5, all right? But if I were to look at all possible samples of size 5, all right, so I got 30 people and I choose 5 of them, okay? So if I do 30, choose 5, so 30, choose 5, I'd actually need 142,506 dots on this dot plot. All right, so this dot plot should have that many dots if it wanted to be an actual sampling distribution. So since we don't have that, it's not a true sampling distribution, all right? So the answer is the above dot plot a sampling distribution, and explain? It would be no. We didn't take all possible samples. We didn't take all possible samples. Okay. Now, number 5 says, we took a random sample of 5 test scores at Rockford High School and got a mean of 68. Is this convincing evidence that Rockford students did worse on their than students at our school, or is it possible that Rockford has the same average? So they give us this other school, Rockford High School, and it's asking us, are they in the same ballpark of ability as we are? All right. Our average was 82.7. Their average was 68. All right. So do we have, obviously 68 is smaller than 82.7. So does that give us convincing evidence that they did worse than us, or was it just random chance that they did worse, right? So anytime you're given a question like this, it's asking, is it possible that Rockford has the same average? All right. So let's just assume that's true. Let's just assume that they do have the same average as us, and they just got a 68 on a fluke, right? Well, if they have the same average as us, then what that means is we could actually take this sampling distribution, this simulated sampling distribution in question 1, and use it for Rockford High School. If they have the same ability as us, then this graph should do a good job representing them, right? So we can ask ourselves, well, what are the odds of someone of the same ability scoring that much lower than us, a 68? So if we come back up to this graph and look, we've got only 1 dot at or below 68. 1 out of the possible 30 we had, right? Which is about 1 out of 30. What is that as a decimal? It's about 3%. 0.3 repeating, so 0.033. Okay, so there's really only a 3.3% chance of Rockford High School scoring that low if they were of the same ability. All right, so there's a really unlikely chance that they're going to be as good as us and still score that low. They shouldn't be scoring that low. They should be up here somewhere with the rest of our samples, right? So it's kind of a stretch to assume that they have the same ability as us when they're scoring so much lower. All right. So the question was, is this convincing evidence that Rockford students did worse than students at our school? I would say yes, it is. This is convincing evidence. All right. And the reason is because if Rockford had the same average as our school, so if Rockford had the same average as our school, it would be very unlikely and in parentheses, I'm just going to put that number. We had 1 out of 30, which equals about 3.3% chance. It would be very unlikely to get a sample mean of 68 or lower. Okay, so if they had the same ability as us, it would be very unlikely for them to get a score that low on this test. Okay, so that gives us evidence to suggest that they aren't as good as us. We're actually better. All right, so a couple important takeaways here. Okay, important ideas. Number one is when you're evaluating a claim, kind of like what we did in question 5 there. We were evaluating a claim that Rockford was better than us. Okay, so number one, evaluating a claim. Evaluating claim, first off, you assume that the claim is true. So number one, assume claim is true. So we assumed that Rockford was as good as us in terms of performance, right? In terms of ability. We looked at, okay, well, let's assume that they actually are just as good as us, but they got that 68 average just on a fluke. All right. But once we assume that, we create a simulated sampling distribution. Okay, so just like that dot plot that we created, we used that to be able to find the percentage chance of getting the observed result. So step 3 is find percentage chance of getting observed result. Okay, so in a nutshell, this distribution right here, this simulated sampling distribution that we have, this shows what could possibly happen just by random chance alone. All right. And then what we do is we take our real life value, in this case 68, and we see what are the odds of that happening. And in this example here, we had a 1 out of 30 chance, or 3.3% chance of that actually happening. If Rockford was actually as good as us, there's only a 3% chance that they would do that poorly on the test. So it's really unlikely that they are as good as us, right? So that's kind of the steps that you want to follow whenever you're looking at a claim like that. The other thing that I want to point out is, so if you're looking at this graph here, okay, so let's just say we have dots looking kind of like this. I'm just going to kind of make a dot plot here. Okay. Now, typically what we'll do is we'll look for that observed result. So like in this case, like for example, let's say we want to look at, did they do better than us? So we would measure everything at and above that value. In the previous example, we were looking at and below because they did worse than us in real life, right? So we usually mark it off at our observed result. Observed result. That's kind of our cutoff point. This is also known as our test statistic. You might see that word thrown around. This is our test statistic. It's our kind of a litmus test. It's where we measure either at and above or at and below the value we want to look at, okay? And we'll typically look at the percent of dots, either at and above or at and below that value. Now, the cutoff point, right? Because we got 3.3% in real life, okay? 3.3%. And we said that resulted in us saying, well, it's really unlikely for that to happen. There's actually a number that we look at for this, and typically it's 5%. Okay. Now, if you have less than a 5% chance, okay, then that means that you have convincing evidence Let me move this really quick. Then that means you have convincing evidence against whatever you're claiming. So in the case of Rockford High School, they were claiming that they were just as good as we were. We showed that there's only a 3% chance of that happening. And so we have evidence to suggest otherwise, right? Now, if your value is at or above 5%, okay, then we do not have convincing evidence. So not convincing evidence. Against your claim. So in the case of the Rockford High School example, let's say we had 10 dots, right? 10 out of 30, that would be a 33% chance. They would have enough to show there's a 33% chance of them scoring just as good as us. So that's a pretty high chance, right? Now, this percentage here, okay, this actually has a name. It's called our significance level. All right, and we typically use the letter alpha to represent it, okay? We usually use 5% as our cutoff. Sometimes it might be 1%, sometimes it might be 10. Different problems might call for different significance levels, but the typical cutoff is 5%. All right, if you ever see a problem that is talking about stuff like this and it doesn't give you a significance level, always just go with 5% as your significance level, right? All right, so check your understanding. It says pennies made prior to 1982 were made of 95% copper. Because of their copper content, these pennies are worth about 2.3 cents each. Pennies made after 1982 are only 2.5% copper. Jenna reads online that 13.2% of pennies in circulation are pre-1982 copper pennies. Jenna has a large container of pennies at home. She selects a random sample of 50 pennies from the container and finds that 11 are pre-1982 copper pennies. Does this provide convincing evidence that the proportion of pennies in her container that are pre-1982 copper pennies are greater than 0.132? All right, so we got a lot of information going on here. The first thing, though, it asks is, what is the population? So remember, population is everybody in the group of things that you're looking at, right? So in this case, we're looking at all pennies in the container. So in container, right? Now, the sample. What sample did she take? Well, it says Jenna has a large container. She selects a random sample of 50 pennies, okay? So our sample is just 50 pennies, okay? Now, what is the parameter, okay? Well, she saw that she reads online that 13.2% of pennies in circulation are copper pennies, right? So that is going to be our parameter. Every penny out there, we assume that 13.2% of them, or 0.32, are made of copper, or pre-1982. And so we use the symbol P to represent this. And then in that sample she took of 50 pennies, she found 11 out of the 50 were pre-1982. So that would be 0.22, all right? and we use the symbol p hat to represent that. Okay. Now it says, does Jenna have some evidence that more than 13.2% of her pennies are pre-1982 copper? Well, if we look, we assume 13.2% are pre-1982, but in her sample, she got 22%. That's bigger than 13.2, right? So we do have evidence to suggest, all right? So we have some evidence. We don't have convincing evidence yet, but we do have some evidence. So yes, in her sample, she had 22%, which is greater than 13.2%. Okay, so we do have some evidence, but was that 22% accurate, or was it just a random chance that she got a really high number, right? So number 3 says provide 2 explanations for the evidence described in number 2. So there's really only 2 reasons why she got 22% instead of 13.2. Okay, so option number 1. It could be that the percent in the container is actually 13.2%. And she got lucky in her sample. You know, maybe she just grabbed a few extra 1982 pennies by accident, right? Just got lucky. So that's one possible reason. Or the other possible reason is that the percent in the container really is greater than 32 or 13.2%. Okay, so it's either that she got lucky and just got a bigger number than what she should have actually gotten, or number 2 possible reason is that the amount in the container actually is bigger than 13.2. All right. Now later on, you might have heard of things called hypotheses in science class, but later on we're going to be talking about this. This would actually be our null hypothesis. This would actually be our alternative hypothesis. All right, so we're kind of breaking ground on what it means to conduct a hypothesis test in a statistics class. Now it says we use technology to simulate 100 simple random samples of size 50 from a population of pennies in which 13.2% are pre-1982 copper pennies. So we're assuming, okay, I'm going to write this out. Assume claim is true. Okay, remember back on the big ideas sheet. So assume claim is true. We're assuming that 13.2% is accurate. Okay, now the dot plot shows p hat, which represents the sample proportion of copper pennies for each of the 100 samples. And so we've got this dot plot over here, right? And each one of these dots represents 50 pennies, 50 randomly selected pennies. And where it lands on the number line tells us the percentage or the proportion of pennies that were pre-1982, okay? Now, it says there is one dot on the graph at 0.22 or 22%. Explain what this dot represents, okay? So Jenna's result was right here. This was Jenna's result. That's what she got in her sample, right? And it's asking us, what does that dot represent? Okay, so this just represents one random sample of 50 pennies. Which had 22% copper pennies. So it's a random sample of 50 pennies where 22% of them were copper. Now, number 5 says, assuming that 13.2% of pennies in circulation are pre-1982 copper, is it surprising to randomly select 50 pennies for which p hat is equal to 22% or greater and justify your answer? So if I look at this, okay, the number of dots at and above 22%, okay, the number of dots at and above 22%. I've got 100 dots total, and only 4 of them are at or above 22%. So that means I've got a 4% chance of getting what Jenna saw in real life. All right. And by the way, this number here, this 4% that we're getting, this also has a name. This is what's known as our p-value or probability value. This value shows us the odds of getting what we saw in real life. Okay. Now it says, it says, is it surprising to randomly select 50 pennies for which 22% or greater are copper? All right. Now, if I go back to the big ideas, if it's less than 5%, we have convincing evidence against the claim. So the claim is 13.2% are copper. All right. So we have a p-value less than 5%. So that means that we do have convincing evidence. So yes, only 4% of the samples had 22% or more that were copper. Okay, so there's only a 4% chance of getting what Jenna saw in real life. And number 6 says, based on your previous answers, is there convincing evidence that more than 13.2% of pennies in Jenna's container are pre-1982 copper pennies, and explain your reasoning? Well, because we have a very unlikely chance of getting what we saw in real life, that means that we're basically saying the reason that she got a 22% isn't because she got lucky. It's because of the alternative hypothesis, is that percent in the container really is greater than 13.2. That's the only plausible reason why we got a percentage that high. So the answer is yes. All right. Now, assuming Jenna's container had 13.2% copper pennies, so assuming the container had 13.2% copper pennies, it's unlikely and in parentheses, I'm going to put 4% chance, 4% to get a sample of 50 with 22% or greater. All right. And so this is kind of just a rundown of, it's kind of the beginnings of doing significance tests in statistics. And so that kind of wraps up what section 7.1 is all about. On the next video, we're going to be talking about section 7.2, day 1. And then after that, we're going to be talking about section 7.3.